Hello students. Hello students. आज का टॉपिक है आज के यूनिट 5 स्टार्ट करेंगे आज हम लोग। यूनिट 5 के टॉपिक्स हैं स्ट्रेन एनर्जी। फर्स्ट ऑफ ऑल स्ट्रेन एनर्जी में हम लोग कास्टिग्लियानो थ्योरम क्या होती है, कास्टिग्लियानो थ्योरम पार्ट 1 पार्ट 2 दोनों हम लोग समझेंगे कि क्या है। उसके बाद लोड डिफॉर्मेशन डायग्राम क्या होते हैं, स्ट्रेन एनर्जी ड्यू टू नॉर्मल स्ट्रेसेस हम लोग डिस्कस करेंगे क्या है, कैसे फाइंड आउट करते हैं, shear stresses, modulus of resilience और strain energy due to bending and torsion। लास्ट में टॉपिक होंगे थ्योरीज ऑफ फेलियर क्या होती है और मैक्सिमम प्रिंसिपल स्ट्रेस थ्योरी, और इसमें मैक्सिमम shear स्ट्रेस थ्योरी को हम लोग डिस्कस करेंगे। ओके, तो फर्स्ट ऑफ ऑल फर्स्ट टॉपिक स्टार्ट करते हैं। इसमें हम कास्टिग्लियानोस थ्योरम। ओके, ओके, what is Castigliano's theorem? Castigliano's theorem, first theorem states that the first partial derivative of total internal energy, known as strain energy, in a structure with respect to any particular deflection component at a point is equal to the force applied at that point and in the direction of corresponding to that deflection component. Okay, explain करता हूँ। Let us consider a beam, a simply supported beam having point loads W1, W2 and W3 at a distance x1, x2 and x3 from the left support A. Now, due to these point loads, the simply supported beam deflects like this. Okay, the deflections at the point first 1 where W1 point load is acting is delta 1, the deflection at the point 2 where point load W2 is acting is delta 2, and deflection at the point 3 where point load W3 is acting is delta 3. Okay, according to the Castigliano's theorem, if total strain energy is U1 plus U2 plus U3 is U. Okay, so according to the Castigliano's theorem, the partial derivative of total strain energy with respect to Castigliano's theorem के अकॉर्डिंग क्या कह रहे हैं, the first partial derivative of the total strain energy in a structure with respect to any particular deflection component at point is equal to the force applied. So the first derivative of total strain energy with respect to deflection let this will be like this. deflection delta 1 will be equal to the load at that point W1. If we partially differentiate this total strain energy with respect to delta 2, then it will be equal to the point load W2. Okay, and last, if we partially differentiate this total strain energy with respect to deflection delta 3, then it will be equal to the point load W3. Okay, now according to the second theorem of Castigliano's, so according to the Castigliano's second theorem, the first partial derivative of total strain energy in a structure with respect to the force applied at any point is equal to the deflection at the point of application of that force in the direction of its line of action. Let a simply supported beam having point loads W1, W2 and W3 and due to these point loads beam will reflect like this, and the deflection under this load W1 is delta 1, deflection under the load W2 is delta 2, and the deflection under the load W3 will be equal to the delta 3. If then in that case, according to this Castigliano's second theorem, the partial derivative of total strain energy with respect to load gives deflection at that point in the direction of force load. So del u upon del w will be equal to the delta 1. Similarly, del u upon del w2 will be equal to the delta 2, and del u upon del w3 will be equal to the delta 3. Okay, this is the Castigliano's theorem. Now second topic is load deformation diagram. Load deformation diagram. What is load deformation diagram? Curve between load and extension or deformation is known as load deformation diagram. Let a gradually increasing tensile force is applied on a bar. Okay, at t is equal to 0, force is equal to 0, corresponding deformation in the bar is 0. So at the starting at t is equal to 0, where force load is 0, deformation is 0. After increasing the load, gradually increasing the load, deformation will also changes according to the load applied on the body. Now the curve plotted between these values is known as load deformation curve. Okay, let's suppose at a point force is F1, so corresponding to this point, this curve, we can calculate we can define the deflection at that particular point. Okay. Now next topic is strain energy. Strain energy. This topic is very important. Now what is strain energy? When an elastic body is loaded, it undergoes deformation. Its dimensions changes, and when it is relieved of the load, it regains its original shape if the force applied at the body or the material is within the elastic limit. For the time loaded, energy is stored in it. The same is given up or released by the loading when the load is removed. This energy is called strain energy. So what is strain energy? Strain energy is a stored energy. Okay, uh, the work done when we applied a load on a body, the work done did by the load is stored in the body in the form of energy. This energy is known as strain energy. Okay, the strain energy stored by the body within the elastic limit when loaded externally is called resilience, and the maximum energy which a body stores up to elastic limit is called proof resilience. So what is strain energy? When we applied a force on a body within the elastic limit, body will goes under some changes, deformation. So work did by this external force is known as force into displacement. This energy will stored in the material in the form of this work done is stored in the material in the form of energy. When the load is removed, then in that case, due to this energy, body will regain its shape. Okay, regain its shape. This energy is known as strain energy. Okay, now the strain energy by the body within the elastic limit when loaded externally is called resilience. So what is resilience? Resilience is known as energy, strain energy stored by the body within the elastic limit, and proof resilience is known as maximum strain energy stored by the body within the elastic limit up to the elastic limit is known as proof resilience. Proof resilience is the mechanical property of the materials, and it indicates their capacity to bear shock. Proof resilience per unit volume is known as modulus of resilience. Modulus of resilience is equal to the proof resilience upon volume of the body. So maximum strain energy stored in a body per unit volume up to the elastic limit is known as modulus of resilience. Okay. Now, strain energy in simple tension and compression. What will the strain energy in simple compression or tension? Okay. Let a tensile force, gradually increasing tensile force, is applied on a body. Okay. Due to which a deformation of delta L is produces in the body. Okay. Let us take the case of a bar cross sectional area A. Okay. We are taking a bar whose cross sectional area is A and the length is L, which is subjected to a gradually increasing load W. Suppose this load extends the bar by an amount of delta L. Due to this external load, the deformation in the bar is delta L. Now, in that case, work done by the load will be equal to the strain energy stored in the body. Strain energy stored will be equal to the work done. Here, work done will be equal to the area under the curve. So here, the area of this curve will be equal to 1 by 2 W into delta L. So, strain energy stored will be equal to U is equal to 1 by 2 W into delta. Okay. We know that stress is equal to the force upon area. Okay. Implies force is equal to the stress into cross sectional area. And we know that strain is equal to the stress upon modulus of elasticity, or strain is change in length upon initial length will be equal to the stress upon modulus of elasticity. From here, change in length will be equal to the sigma into L by E. Now, putting these value in the equation, strain energy will be equal to 1 by 2 sigma into A into sigma into L upon E. So from here U will be equal to the 1 by 2 sigma square upon E into A into L. Here A into L is volume of the bar. So U will be equal to the sigma square upon 2E into volume of the bar, or U upon strain energy upon volume will be is equal to the U sigma square upon 2E. If the load applied on this bar is up to the elastic limit, in that case modulus of resilience will be equal to the sigma square upon 2E. Okay, sigma square upon 2. Now strain energy due to the pure shearing strain energy due to pure shearing or due to the shear stress. Okay, consider a rectangular block of material subjected to shear force F. Let A, B, C, D. Consider a rectangular block of unit length, unit depth ABCD of material subjected to shearing force F acting across two of its opposite faces. Okay. The face AB will move relative to DC a distance BB dash. Okay. Here BB dash will be equal to the BC into phi. If this angle phi is very small, in that case tan phi is equal to the phi. So from here right angle triangle BB dash C, BB dash will be is equal to the BC into phi. Okay. Now the work done by this shear force will be equal to the work done by the shear force will be equal to the 1 by 2 into F into deformation. Deformation is BB dash. If here the shearing force is greatly increasing force, in that case the work done will be equal to the 1 by 2 F into BB dash. We know that BB dash is equal to the BC into phi. Okay. Work done. Equation 1. We know that shear force will be equal to the shear stress into area AB, and shear strain is equal to the shear stress upon modulus of rigidity. Now putting this value in equation number 1, work done will be equal to the one by 2 tau into AB into Vc into tau upon g. It will be equal to the tau square upon 2g into AB into BC or into 1. AB into BC into 1 is the volume of this body. Then in that case, total work done or total work done is equal to the strain energy. So strain energy per unit volume will be is equal to the tau square upon 2g. Strain energy per unit volume is known as modulus of resilience. So in the case of a pure shearing, modulus of resilience will be equal to the tau square upon 2g. Okay. Now strain energy, next topic is strain energy in torsion. Okay, let us consider a shaft of length L and radius R, subjected to a torque T due to this torque, angle of twist is theta and solid angle is phi. Okay, now due to this torque, work done will be equal to the 1 by 2 T into the theta. This is the equation number 1. From torsion equation, T by J is equal to the tau by R into G into theta by L. Okay. Now from here, T is equal to the tau into J upon R, and theta will be equal to the tau into L upon G into R. Putting these value in equation number 1, work done or strain energy, say strain energy is equal to the 1 by 2 into tau into J upon R into tau into L upon G by G into R. Now from here, strain energy U is equal to the tau square upon 2G into R square into J -12. ठीक है, okay. We know that J is equal to the pi R to the power 4 upon 2. Okay. Now putting this value in this equation, u will be equal to the tau square into L upon 2gr square into pi r to the power 4 upon 2. Now from here u will be is equal to the tau square upon 2g into pi r square by 2 into L. This is the volume of the shaft. So strain energy upon volume is known as is equal to the tau square upon 2g. Okay. So from here, modulus of resilience due to the torsion will be equal to the tau square upon 2g. Now come to the next topic, strain energy due to the bending. Strain energy due to bending. Let us consider a beam of uniform cross section let us consider a layer at a distance y from the neutral axis of thickness dy. Okay, suppose A, B, C, D will be the strip. Okay, if width of the cross section is B and length of this section, this layer is dx. Okay, in that case strain energy on this section will be equal to the sigma square upon 2 into volume of this section strip. Now what will be the volume of this section? It will be equal to the dx into dy into b. Okay, this is the volume of this section. Now from the bending equation we know that m upon I is equal to the sigma upon y is equal to the E by R. Now from this bending equation, sigma is equal to the m into y upon I. Okay, Now putting this value in equation number 1, u will be equal to the my upon I square 1 upon 2e v into dx into dy. Okay, this will be the strain energy on the string. Now the total strain energy on the section will be integration m square y square upon 2e into I square into b into dx into dy. Now m square into dx upon 2e into I square is common, constant. Okay, b into y square into dy. Integration b into y square into dy will be is equal to the second moment of area known as moment of inertia. So it will be equal to the I. Now strain energy will be is equal to the m square upon 2ei into dx. Okay. The above expression gives the strain energy of the beam of for dx beam on d for the dx length. So the strain energy for whole length of the beam will be is equal to the m square L upon 2ei. This will be the strain energy due to the bending moment. Okay, strain energy due to the movement. Now next topic is okay. We have discussed Castigliano's theorem first and second, load deformation diagram, strain energy due to normal stresses, shear stresses, modulus of resilience, strain energy due to bending and torsion. Now the last topic is theory of failure, maximum principal stress theory and maximum shear stress theory. Okay. Now what is maximum theory of failure? Okay. So first theory is maximum principal stress theory. Yes, maximum principal stress theory. Now what is maximum principal stress theory? Let us consider a body subjected to three mutually perpendicular stresses acting in x, y and z direction, sigma 1, sigma 2 and sigma 3, and elastic limit of this material is sigma E. Yield stress of this material is sigma E. So according to this maximum principal stress theory, failure will occur when the maximum principal tensile stress in the complex system reaches the value of maximum stress at the elastic limit in simple tension, or the minimum principal stress reaches the elastic limit stress in simple compression. Okay, let here sigma 1 is greater than sigma 2 and greater than sigma 3. In that case, sigma 1 is the maximum principal stress. Okay, so according to the maximum principal stress theory, failure will occur if sigma 1 is greater than or equal to the sigma E. Okay, so according to this theory, failure will occur when the maximum principal stress sigma 1 in complex system reaches the value of maximum stress at elastic limit. Sigma E in simple tension. Okay, this is the simplest and oldest theory of failure. This theory is also known as Rankine theory. This theory is also known as Rankine theory. Okay, now come to the next theory of failure. Maximum shear stress theory. Maximum shear stress theory. Okay, this theory implies that failure will occur when the maximum shear stress in the complex system reaches the value of the maximum shear stress in simple tension at the elastic limit. Okay, according to the maximum shear stress theory, if three mutually perpendicular stresses are acting in xyz direction, sigma 1, sigma 2, sigma 3, and sigma 1 is greater than sigma 2 and this is greater than sigma 3, in that case maximum shear stress will be equal to the sigma 1 minus sigma 3 divided by the 2. Okay, so this theory implies that according to this theory failure will occur when the maximum shear stress in the complex system reaches the value of maximum shear stress in simple tension. If this is equal to the sigma, let's say tau e. Here tau maximum is sigma 1 minus sigma 3 by 2 and tau e will be is equal to sigma e by 2. So sigma 1 minus sigma 3, if greater than or equal to the sigma e, in that case failure will occur according to the maximum shear stress theory. This theory is also known as Guest theory or Tresca theory. Guest or Tresca theory. Here sigma 1 is the maximum stress, principal stress, and sigma 3 is the minimum shear stress. If this is equal to the sigma equal to the greater than equal to the sigma e, in that case failure will occur. Okay. Now, what is factor of safety? Last topic is factor of safety. Okay. Factor of safety or FOS is equal to the maximum stress upon working stress. What is maximum stress? Maximum stress can be yield stress, ultimate stress, okay, and working stress is the stress at which maximum stress can produce in a body under the load conditions where the material is used. Okay, let suppose a cable is designed for a lift. The yield stress of the material of the wire is 200 Newton per meter square, and the load applied on this cable, okay, if the maximum load applied on the cable is W, and due to this maximum load the allowable or working stress is 100 Newton per meter square. Here the maximum load can be applied on the lift is W, and due to this maximum load working stress is 100 Newton per meter square in the cable. In that case, factor of safety of this cable is 200 upon 100, it means 2. Okay, this will be the factor of safety of the material. Okay, uh, thank you so much. This unit is completed today. Okay, thank you so much.